So, in the previous lecture we have considered free gravitational waves and the energy carried by them, energy flux carried by them. In this lecture we continue the consideration of the gravitational waves, but we concretely consider waves that are created by massive bodies, moving massive bodies. We have to solve the following equation. Box psi mu nu equals to 16, approximately equals to 16 pi kappa t mu nu, and d mu psi mu nu equals to 0. I remind you that psi mu nu is h mu nu minus half traceless part of this is h, and h is actually alpha, trace part of h. And in this expression we keep, of course there are terms which are of higher order in h, nonlinear terms, that are in particular contained in the gravitational pseudotensor, energy momentum pseudotensor. And then here we contain only linear in h terms. And one comment is in order here, that the gauge condition here is in the agreement with the conservation, in linearized approximation, conservation of this energy momentum tensor. So, to solve such an equation, one has to use so-called green function. Green function for the box operator. This is D'Alembertian operator. Yeah, probably I have to define that box is dt squared minus Laplacian. So to solve this equation, we have to use D'Alembertian green function for the retarded green function for the D'Alembertian operator. Retarded green function. So I assume that all the listeners of my lectures are familiar with the standard course of special theory of relativity and classical electrodynamics, where people study the standard electromagnetic radiation, and hence they are familiar with such a notion as a green function and how to find solution of such equations with the use of the green function. So the green function solved for the box operator, for the D'Alembertian operator, solves this equation: 4 pi delta 4x minus y, where x bar is just 4 vector, and y bar also. It's so t and x vector, 4 vector. So this is a product of 4 delta function. Delta 4 of x is a product of 4 delta functions for each component of x and y. And the solution of this equation should be known to those who are familiar with electromagnetic radiation. Retarded solution of this equation is as follows: theta function of tx minus ty times delta tx minus ty minus x minus y modulus divided by x minus y modulus. So theta function is a Heaviside theta function, so theta of delta t is equal to 1 when delta t is greater than 0, and 0 when delta t is less than 0. And well, before moving further, let me clarify the physical meaning of the retarded green function. So as one can see from this delta function, retarded green function, in fact, so we have a point y, 4-point y, so this is a space-time t, x1, x2. So this is point y, which is a source here. And green function basically gives you the value of the field which is sourced at the point y. So there is a light cone which has this point y as a apex, and we have due to this theta function this retarded green function is not zero on the light cone, on the future light cone, starting from y, from the point y, from the event y. So this is at any point x laying on this light cone, this function is not zero. So basically, if we have this function which solves this equation, then the solution of this equation can be represented as follows. So it's psi mu nu of t and x is approximately equal to 4 kappa integral over d3y t mu nu y t minus x minus y divided by x minus y modulus. So how did I obtain this? Well, basically psi mu nu is equal, that solves this equation, is equal to minus 16 pi kappa integral over d4y g retarded x minus y t mu nu function of y. And then I took one of the integrals of this. There are 4 integrals here. I took the integral over ty, one of the integrals, with the use of this delta function. And that's how I obtained this expression. So now we have this solution at our disposal, and we're going to use it. So actually, physically, it describes the following situation. There is basically a source, which is just some collection of bodies moving somehow. So this is just a bunch of bodies which are responsible for this energy momentum tensor. And at each point x, which if there is an act of creation of the radiation at every point, so there is a light cone starting from any point where the source is, and we can observe radiation at every point x created somewhere by the bunch of bodies that are responsible for this energy momentum tensor. So this is the physical meaning of the obtained expression. Well, anyway, everybody who has studied electromagnetic radiation should know this. So I just give a small comment. So now we are assuming the following situation, that this is a physical meaning of this formula. After the integration over t, the physical meaning is not that obvious, a bit less obvious. So now I assume that the region where the body, where the energy momentum tensor is not zero is compact. So I assume that there is some volume in space, where the bodies are moving. There is a motion, complicated motion of bodies. So this is a region V. And we want to observe the creation of radiation in a very far distance. So the region where y takes values, y, is here. And we want to observe the radiation that is created by these particles very far away. So such that modulus of x, so the origin of the coordinate system is somewhere here. So we want to consider such a situation that all values of x are much greater than y. So we are in the so-called wave zone. Then one can immediately, at the leading approximation, neglect y in the denominator. And the situation is such that to neglect y here in numerator, one has to consider a so-called non-relativistic motion of the bodies. If the motion is non-relativistic, one can neglect y here also. Then, in such a situation, we are basically considering the following solution. Let me write it. Well, before writing it, I should state that if we are very far from the source of the radiation, in that region, T mu nu is 0. So basically our psi solves homogeneous equation, the same kind of equation as we have been considering in at the end of the previous lecture. And hence, that solution has similar properties to those which we have encountered in the previous lecture. In particular, one of the properties is such that it's traceless. So it means that H alpha alpha is 0. Free gravitational waves, as we remember, are traceless. As a result, H alpha alpha is 0. And hence, we have such a situation that psi mu is basically equal to H mu. And also, we have only spatially directed components. So only non-trivial and non-zero components are Hij, as we remember from the previous lecture. As a result, taking into account all these statements that I have made, the solution that we are going to work with is as follows. Hij is approximately equal to minus 4 kappa divided by modulus of x, that is due to the denominator, times the integral over the compact volume d3y times tij, which is a function of t, the same, this is t and x, function of t and x, is a function of t and y. So remember, we have neglected y here in this expression, and that's how we get this solution. That's it. So we're gonna work with this expression. So we have obtained the following expression for the radiation field, gravitational radiation field. I have to correct the last formula, which I have just obtained a little bit. The correction will be obvious. So we have modulus of x here, integral over d3y over the volume where the energy momentum tensor is not 0, and argument of t is actually t minus modulus of x, y. So this is an observation moment, and this is a radiation moment. So let me draw the picture again. There is a radiation moment defined by y if the bodies are moving non-relativistically, so we neglect here the argument of y, and the observation moment is somewhere here, and the moment of radiation is light-like distance away from here in the space-time. Okay, anyway, so this is the expression we obtained. Again, this expression is obtained in non-relativistic approximation and very far away from the region where the energy momentum tensor is not 0, very far away from in the wave zone. So to study in greater details the limits of validity of these formulas and the way one obtains these formulas, one should consult the standard electromagnetic radiation. The situation is very similar. One can say, read that in Landau-Lifshitz second volume. Anyway, so here, the problem with this formula is Tij here depends on the details of motion of radiating massive bodies. And we want to, so it doesn't just depend on the mass distribution or these kind of things. So we want to do some manipulation to express this quantity through the details of the distribution, not the details of the motion. So we will do the following trick. Let us consider the conservation of this spatial part of the energy conservation. So this conservation law. Multiply it by Ij and integrate over dy. So as a result, we obtain the following, that we have the following expression equal to 0. So if we multiply by ij and integrate, we get 0. So it's yj d mu t mu y. So, and rewriting this as d3y yj dt t0I minus dk tki. Now, in this expression, we can make the integration by parts and drop off the boundary terms. Well, as usual, we drop off in this lecture course. We ignore the discussion of the boundary terms, which is a separate subject. But we assume that everything is vanishing, all the fields and masses, fluxes, well, not the fluxes, all the currents are vanishing at infinity. So when we integrate by parts, we obtain boundary term, which is at partial infinity, we drop it off, and the remaining volume term gives us the following expression. So continuing that equality, we obtain the following situation, that dt, well, here we can take dt from, take out from the integral, so d3y yj dt, oh sorry, not dt, no dt here, dt is taken away, ti I0, plus, after integration by part, d3y tij. So after integration by part, the derivative acts on this. We get a Kronecker symbol, and which makes k equal to j. So this is actually the expression that we have here. And we have that it is equal to this. And then one can, because Tij is symmetric, on the exchange of indices, as a result, we have the following equality, that the integral over d3y of Tij is equal to minus 1/2 times dt of the following expression, d3y yj t0I plus yi t0j. Well, this is easy. This is times. Okay. So let us move further. Let us multiply now time. So we have also, apart from this, we have also t mu 0 of y equal to 0. Let us multiply this by y k and yl, and again integrate, take the integral. As a result, we get the following expression, that to 0 is equal the following expression, d3y yk yl d mu t mu 0. Again, doing the same here as we did here, so expanding this. We expanded this expression like this, so we can expand this expression like in similar manner. As a result, we get dt acting over on d3y yk yl t0 0 plus integral over d3 y yk t0l plus yl t0k after integration by part. After integration by part in the second term. So this is exactly the same expression as we get here. As a result, combining these two formulas together, we obtain the following expression, that integral over d3 y tij is minus 1/2 double derivative over t of integral over d3 y t0 0. Now, using this in here, we obtain that Hij is approximately equal to minus 2 kappa over modulus of x times dt squared over d3 y yj t00. This expression already depends only on mass. This T00 is nothing but the mass density. Now, having in mind that Hij is traceless, we can subtract from this expression its trace, and as a result, we get the following expression, final expression that we're going to use in the following, final expression for the radiation field. 2 kappa over 3 modulus of x times Qij, where Qij is the quadrupole mass moment, because it is equal to the following quantity, d3y times rho times 3y yj minus delta ij y squared. Basically, we multiplied this by 3, divided by 3, and then subtracted from this expression its traceless part. So here is a double derivative. So this is a final expression that we get. The final expression that we get. Now, it can be explained on general grounds that why should we expect such an answer? Remember that for electromagnetic radiation, we have a vector field. Its spatial component is the first derivative of the dipole moment. So it's not so unexpected that for tensor field, we have a second derivative of a tensor quantity. The other way to observe it, of course, it's a very heuristic and vague explanation. The second reason to expect something proportional to quadrupole moment in case of gravity is the following situation. In case of electromagnetic radiation, we know that if the gyromagnetic ratio E over m is equal to 1, for such a system where this gyromagnetic ratio in electromagnetic case is the same for all charges contributing to the radiation field, if it is the same for all charges contributing to the radiation field, then dipole radiation and magnetic dipole radiation are vanishing, and the only contribution to the radiation process in electromagnetic case is quadrupole contribution. But in case of gravity, we have basically charge proportional to the mass, because what is charge for gravity is a mass. So this ratio for the gravity is also always equal to 1 and the same for all sorts of radiating bodies. And as a result, it's not such an unexpected fact that radiation field in gravity is proportional to the quadrupole moment. Now we're going to use this expression to calculate intensity of the gravitational radiation that is created by moving bodies.